this is the last session of today, as you know. As I said, we have 5 talks, 1 invited and 4 contributed. So for the speakers, I just remind you that an invited talk is 30 minutes, including questions. The contributed talks are 15 minutes, including questions. And so try to be on time. And for the audience, if you want to ask questions, you can write them in the chat and I can repeat for you, or you can just unmute and speak for yourself. Okay, so I think we can start now. So our first speaker is an invited speaker, so Francisco Correia dos Santos. Did I say it well?
Yes, perfectly.
Okay, great. So the title of the talk, you can see it. So climate action, cooperation, and institutional approaches to governances, to the governance of risky commons. So the stage is yours, Francisco, please.
So thank you so much, Giulio. And I'm very happy to give this presentation here. Thank you so much for the invitation. So today I would like to speak about cooperation, as the title says. So I normally, one of the topics that I normally work is to understand how cooperation can emerge, both in simple societies, but also among humans. And today I would like to be slightly more ambitious, and I would like to build on the words by Simon Levin a few minutes ago and try to discuss cooperation that we normally have to face, or we need to face when we speak about climate action and climate governance. Of course, I'm not going to provide any solution to this complex problem. I will start by showing some results, some simple models and experiments that help us to understand the complexity of the problem that we all face. So please interrupt me whenever you feel like. We are a small room, so I'd be glad to answer your questions if you feel like interrupting. So let me highlight that this talk combines the thoughts and the discussions with several of my colleagues, and you'll see their names and their photos popping up in each case. So to give you an overview, I'll start by providing some game theoretical approach to this problem. Then I will discuss some experiments and models that we have been dealing in the working on last months related with uncertainty and the impact of uncertainty in this complex dilemma. And then I will follow to the problem of institutions that are stable enough to ensure cooperation in the long run. And if I have the time, I will also show you some recent experiments that we have been dealing and working on the impact of technology and artificial entities on the very same class of dilemmas. So whenever we speak about climate change and climate action, we often end up discussing this idea of public goods or public goods gains. So the idea is very simple. You normally have a group of individuals that can, for instance, contribute or not to a collective investment that will later on be expanded, and the profits will be equally shared by everyone who participated, irrespectively if they contributed or not. So in this context, it's very easy to see that free riding on the effort of the others will be the most profitable situation. If everyone thinks the same thing, we will get to the famous tragedy of the commons that Simon has highlighted in a few minutes ago. The problem of climate change has this additional feature, this additional difficulty that we are cooperating somehow with the future. So we are cooperating not with us, or we are cooperating with someone, our sons, our grandsons. So we have, or if you wish, the returns will be only obtained later on your life. So this creates an additional complexity to the problem, at the same time that highlights the fact that we are dealing with a problem that we have never faced, especially given the dimension. We are dealing with the global common. So the things start to be much harder to manage. But to provide you with an idea, I will show you some experiments that have been dealt or have been proposed by Manfred Milinski and colleagues in 2008, and since then have been used in several experiments to deal with this very same problem. So you can imagine an experiment, an economic experiment, where you have 6 players, each player receives 40 euros, and they play in a game that lasts for 10 rounds, and in each round, each player has the possibility to invest 0, 2, or 4 euros. So if at the end of the 10 rounds you get to 120 euros, you can say that metaphorically the planet will be saved and everyone will go home with the money left. So the goal here will be to invest to reach to the 120 euros, but you also may think that the others could do the effort for you, and you start free riding on the effort of the others. So if the group doesn't reach the 120 euros after the 10 rounds with a given probability, you may have a disaster, and with a given probability, and everyone will lose whatever they have. So the goal here will be probably to invest as less as possible, but nonetheless to get to the 120 euros. These experiments provide several interesting indications on decision making, but one of the important things here is that the percentage of groups that manage to reach to the threshold is strongly dependent on the risk, this probability of losing everything. So if the perception of risk is large, then people start to contribute more. So it's not so hard to get to these results from a theoretical point of view. You can immediately see that we are dealing with a public good game that differs from most of the games that people normally discuss. So instead of having a linear increase in the returns with the investments made, we have a kind of step functions. We have a coordination game, a collective, an n-person collective game, a coordination game. So in the simple setting, you can imagine groups of size m, a threshold of m, where you have cooperators and defectors. Cooperators contribute a fraction of their initial endowment, defectors do not contribute. And if the sum of all the contributions surpass this threshold, everyone will keep whatever they have. Otherwise, they lose whatever they have with a given probability. You can imagine that you have a population, in this case, students that are sampled. So groups are sampled from a large population. You can also imagine that you can also check the experiment and see that most of the people will revise their strategies along the way. So they are not really playing some sort of Nash equilibrium. They are very much influenced by what the others did and revise their choices accordingly. So instead of using classical game theory, for this reason, we decided to resort to an evolutionary approach to this problem. So instead of having a static game, we have an evolutionary game theory framework which allow populations to evolve and to highlight the ecology of strategies that emerge from this process. So here the idea is that the payoff is associated with fitness, and if you are playing with genetic evolution, you can imagine that individuals with higher fitness will produce more, but in this case, fitness is associated with some sort of social success, which means that strategies that have a higher social success will be imitated more often and spread throughout the population. This is also interesting to see that this also relates very well, and it can be shown to be equivalent to some sort of reinforcement learning. So you can imagine that at each time step, each individual imitates another random individual with a probability that increases with the fitness difference. This probability can take many forms. Here I'm using a Fermi function, but also you can also introduce some sort of exploration probability, a kind of mutation probability. The important thing here is that at the end, you get to a Markov chain that basically tells you the probability of increasing or decreasing the number of each strategy, and from this Markov chain, you get the stationary distribution of the most likely configurations. So if you do so, you reach the situation where you can show that the group achievement, so meaning the probability of the fraction of groups that succeed to reach the threshold, increased very much like the experiments with the probability of failing or the perception of risk. Moreover, you can go beyond the experiments and actually figure out the group dependence of this game. And the group dependence here is very important given that it defines the scale at which these agreements should be discussed. So what I'm showing you here is that not only group achievement, the probability of success increases with the perception of risk, but also tells you that when you increase the group size, the chances of success decrease. So basically, when I'm saying that I'm increasing the group size, I'm pushing the group size to the size of the population, which means that when n is equal to z, it means that the entire population is sit in the same room trying to find an agreement. And this is exactly what we are trying to do in climate summits. So what this game theoretical approach suggests is that instead of going for one global agreement where everyone is sitting in the same room trying to find an agreement, we'll be better off by discussing this problem from a polycentric point of view, where we have multiple small-scale agreements. This is also interesting because you can actually show why this happens. And from a dynamical system point of view, it's interesting to see that when you have large groups and a low perception of risk, the chances of getting to cooperations are very small. So basically, irrespective of where you start, you always end up with a small fraction of cooperators. However, when you increase the perception of risk, or if you consider small-scale groups, small-scale agreements, then you transform the game, the previous dynamics, into something that is defined by an unstable and then a stable fixed point. This is much easier to solve, given that you only need to overcome this coordination barrier to get to stable coexistence of cooperators. It's also important to see that this is not actually a very new idea. This is actually an evolutionary perspective of the idea of polycentrism that has been pushed for by Elinor Ostrom. So the idea is that you have a global problem doesn't mean that you need to deal with it at a global scale as well. You can deal with it at multiple scales. And for instance, you could, for instance, build small scale groups that manage to cooperate and grow from that. This is the idea of the coalition formation that, for instance, Vitor Vasconcelos and Simon Levine, Jorge Pacheco, and Phil Hannam proposed a few months ago in a scientific reports paper, that we have coalitions that can grow in size. So can we improve cooperation even further? So by doing this, you need to perhaps tackle more complex scenarios. So for instance, here I'm showing you some of these scenarios that we have been dealing with. So for instance, the first one is related with uncertainty. So uncertainty is a key idea here because we can have uncertainty, scientific or political uncertainty in many of these parameters that I've been telling you about. So for instance, the threshold that I told you, these 120 euros, if you say that you need more or less 120 euros, it has been shown both theoretically, but also experimentally that basically destroys cooperation. But other important thing is the idea of timing uncertainty. The fact that you don't know exactly how much time you have to solve the problem. So if in the original experiment, I told you that we have 10 rounds, or individuals had 10 rounds to solve the problem. However, in reality, we don't really know when the game ends. So a few months ago, we decided to build up an experiment, a lab experiment on this idea, where we have 3 treatments. So we have the first experiment, so basically reproducing the same ideas by the original experiment by Manfred Milinski, where we have a fixed number of rounds. Each individual could contribute 0, 2, or 4 euros. And at the end, if you get to the 120 euros, everyone will be happy and take the rest of the money that they have on the pocket home. In the second experiment and third experiment, we start to introduce some level of uncertainty. So for instance, the game will finish with the probability of 1/3, or the game will finish with the probability of 1/5. The important thing is that in all cases, the average number of rounds remain the same 10. Okay. So what we have shown is that the chances of success, of reaching to the threshold, will decrease with uncertainty. This is not so surprising given what I told you before. So when you have no uncertainty, the fraction of successful groups will be maximum. However, more surprising results came if we start to dig into the results. So the first thing that we immediately saw is that if you analyze the contributions per round, you see that in the absence of uncertainty, people would contribute more or less what will be fair. So fair means that if everyone contributes €2 in each round on average, you'll get to the 120 euros. So there is a fair division of the effort by all group members. What happens is that when you start to have uncertainty, individuals start to play, or they look to play as a risk-averse agent and start to invest earlier. So individuals, when facing uncertainty, they react by investing more at the beginning. However, not all did this. In fact, what you can see is that this is the 3 treatments. So the first one is no uncertainty, low uncertainty, and high uncertainty. What we found out is that uncertainty leads to polarization. So what happens is that in the absence of uncertainty, most individuals would contribute a fair amount. And when we start increasing uncertainty, what happens is that this fair amount, the number of individuals contributing this fair amount, will be reduced. And you have more individuals contributing more than they should, contributing, for instance, €4 in each round, and others that free ride on the effort of these altruists. So by adding some uncertainty, you have polarized behaviors popping up immediately from this game, this very simple game. We also realized that the type of strategies that emerge are very much different when we start to have uncertainty. So in the absence of uncertainty, most individuals will be more or less, they didn't care much about the average donation in the previous round. So people will not really reciprocate the actions of the others. But in the presence of uncertainty, what people start to do, they start to retaliate what the others did. If the others are contributing a lot, they will follow the lead and follow this movement. However, if the other persons in the group start to contribute less, they will also contribute less. Based on these results, we pick the experiments and start to cluster the strategies using standard data science techniques, and realize that we can group behaviors in many different ways. Basically, you can group all the players in 5 main strategies. So you have individuals that are always playing the fair one, the fair contributions. You have other individuals that free ride on the efforts of the others. You have other individuals that try to solve the problem as fast as possible, contributing €4 until the problem is solved. And then you have some compensators, individuals that essentially they only contribute if things are not going well. And you have reciprocators that basically follow what the others are doing. And the interesting part is that if you analyze the population dynamic, this game theoretical analysis, using these 5 strategies, you basically recover the results that you obtain in experiments. So you can, for instance, see that group achievement slightly decrease with uncertainty. So here is the group achievement as a function of these 3 treatments. So no uncertainty, low uncertainty, and high uncertainty. You have an increase of reciprocity-based strategies with uncertainty, and you get the polarization as before. Interesting, we also analyze how the game changes. So in practice, when you have low uncertainty, basically you have 2 equilibrium strategies. So we have the fair strategy and the free riding strategies. And when you start to have uncertainty, things start to be very much complicated, much more complicated. You start to have something like is similar to a rock, paper, scissors game with cycles and stuff like that. So the nature of the game is slightly transformed. So we can also analyze other more complex scenarios where you have conflicting policies between rich and poor parties. So the role of wealth inequality is very important because in fact, people are not really playing the same game. So what we have done is to analyze this very same dilemma where individuals at the start, they do not all start with the same initial endowment. Some have more money to invest and some others have less money to invest. And what we have shown is that you may have some cycles between the fraction of cooperators among the poor and the fraction of cooperators among the rich, figuring out that actually this wealth inequality, you can take profit from this wealth inequality as long as the poor and the rich are well mixed in their groups. So if you start to split groups of rich and groups of poor individuals, if you have individuals, the rich only imitate the rich and the poor only imitate the poor, then this positive feedback is completely destroyed. So it's very important to have these groups mixed up. Finally, one of the things that we have been working most is this idea of institutions. So institutions are very important when we are dealing with these complex problems. And when you open the Pandora box of institutions, there are several problems that pop up. First of all, these institutions, they are not always stable. So when we have institutions that are able to punish those that do not contribute what they should, for instance, and these institutions are often costly, leading to a second order free riding problem, just like you have another public good game on top of this. The second point, or the third and fourth question, is related with the scale of these institutions. Again, we can have a global institution or a local institution, and it's not really easy to see what is the best layout of these institutions. So we have sanctions, should we have rewards, should we have more complex scenarios? So to have an idea, let's imagine that I have cooperators and defectors as before, and I add a third strategy here, which I'm calling it punishers. So cooperators and defectors work as before. The cooperators pay a fraction of their endowment, defectors do not. And punishers basically are just like cooperators, but they pay an additional cost to create an institution that if there is a minimal number of contributions of P's like these punishers, then this institution will start to punish the defectors. And these work quite well, especially for instance, if you imagine that if you have punishers playing with defectors, these institutions will work very well, and start to punish defectors, and cooperation will arise. The problem is that if cooperation arises here, there is no need to have an institution, and these, let's call second order free riders, will emerge and will replace these punishers, and in the absence of punishers and institutions, the defectors can evolve again. So from these cycles, it's pretty easy to see that we have a second order dilemma. You have to solve the second order free riding dilemma. Actually, if you analyze this in more detail, you see that we have exactly that. So in the simplex, you have a population of punishers, cooperators, and defectors. Arrows means the most likely direction of evolution. And this gray scale here is the stationary distribution. It's basically where the systems spend most of the time. So in this corner, we have 100% of defectors, 100% of punishers, 100% of cooperators. Here in the middle, we have 33% of each of the strategies. It's pretty clear that if for some reason punishers evolve, and then cooperation will be happy and will be very high, but it's pretty likely that afterwards the cooperators, those that do not contribute to form the institution, will emerge, opening the door for defectors. So this is the case where the institution is global. So you need to have 25% of the entire population contributing, and if you have 25% of the population contributing to form an institution, all defectors in the population will be punished. However, you can solve this problem mildly by considering multiple local institutions again. So here, the idea is that you have institutions that only work locally. It's very easy to coordinate, but they also only punish those defectors that are inside these groups of size n. So in this case, you can have some institutions working, and cooperation will increase likely, but the problem is, again, the fraction of institutions that are working are very small. Basically, all the punishers are wiped out from the population. So you only have a few that are somehow manage to have some institutions working. So to a large extent, we fail at creating self-sustained or stable institutions in this context. So how can we overcome this second order free riding problem that I've been telling you about? So one thing that we tried is to replace punishment by rewards. So the idea here is that each institution has some budget, and they can use the same budget, either to reward or to punish. And what we can see is that in this particular case, in this particular dilemma, this is not always the case. Some other dilemmas, punishment works very well. In this particular case, rewards work better than punishment. Here I have the fraction of groups that succeed in surpassing the threshold as a function of risk, as usual. And the black line here is the reference scenario where you don't have punishment. And as you see, rewarding institutions work pretty well and can actually improve cooperation for values of the perception of risk that are very low. The reason behind this is that if you pick the setting that I was telling you about, where you have a coordination or unstable fixed point that you need to overcome and a coexistence point here, what happens is that rewards move this coordination point closely to the point where the percentage of cooperators is very small. This makes it very easy to surpass it through stochastic effects and others, and the population will end up here in this coexistence between cooperators and defectors. Punishment or sanctions work in the opposite way. They work by moving this coexistence to the right. So the fact is that both rewards and sanctions work very well. The point is that rewards are crucial when cooperation is low, which is the case now. So basically allowing the population to surpass this coordination barrier, while sanctions are really helpful if you feel like maintaining the high levels of cooperation whenever you already have it. And this is very important and interesting result. So it becomes very hard to return back to the tragedy of the commons. Yet, even if efficient, these rewarding institutions remain largely unstable. So how can we solve this? So a few minutes ago, I told you about the work by Elinor Ostrom, pushing forward the idea that a polycentric structure of agreements could work better than one single agreement. This is one of the famous design principles proposed by Elinor Ostrom. However, there are several other design principles that can be very helpful in this context. Another one, which I find it really, really interesting, is the idea that punishment should be graduated. What does it mean? It means that sanctions the severity of the sanction should increase with the harm caused by the defector. So for instance, instead of having a strict penalty, the penalty should grow with the damage that the defectors created. So if after a while, if basically the defectors do not prevent the group to reach to the threshold, maybe the punishment or the sanction shouldn't be so high. And that's what we tried out. And we figured out several variants. Of course, we could have graduated sanctions and strict costs to the punishers. You could also have graduated sanctions with graduated costs. And clearly what we see is that this idea proposed by Elinor Ostrom is pretty efficient in this type of dilemmas. Actually, we can show that what happens is that by having graduated sanctions, we create an edge of neutrality between cooperators and punishers, which allow institutions to remain working most of the time. This is a very interesting way out to create institutions that are self-sustaining, but also we are able to solve the very famous second-order free riding problem using the insights, one of the many insights provided by Elinor Ostrom. And again, these settings work very well, especially when you have small-scale institutions. So where you go from here? So if I still have 2 minutes, do I, Giulio?
Yes.
So if I have 2 minutes, let me also share with you some results that we are also having when we extend these to more complex scenarios, where we not only have individuals, say humans, trying to figure out a way out to these type of dilemmas, but when these populations of humans are mixed up with algorithms and artificial agents, as we are currently facing. So these artificial agents or entities do not need to be robots, but could be simply algorithms that are interacting with us in some way. So these hybrid societies that we are living create several interesting dilemmas or research questions. And for instance, we have shown that, for instance, if you have an hybrid population where you have a few individuals introduced there that are pre-engineered to work in a certain and in particular way, it can happily nudge the entire population to be more cooperative at a global scale. Moreover, you can also ask what would happen if individuals, instead of playing themselves, they start by delegating their choices to these artificial agents. This is another form where hybrid populations could play a role. So we actually did some experiments on this regard, where we have exactly the same collective risk dilemma that I told you before, this public good game, where individuals, instead of playing, they basically select a robot, or they program a robot that play on their behalf with their own money, with the money that the humans received. And what we have shown is that this has a particular impact on the level of cooperation that we have. So whenever individuals delegate their choices, apparently they are pushed to discount the future in different ways and become more cooperative. And these results show that by delegating, cooperation will increase if you have some sort of these robots that play on your behalf. So of course, the goal here will not to try to solve this very complex problem using this complex pro-social robot, especially because we have to be careful about the externalities or the unintended effects of mixing up humans with robots and artificial entities. It's very important to keep in mind where the problem is, and clearly the problem is on the human behavior. But I think it's a good point, a good place to stop here. And thank you so much again for your attention and for the opportunity to speak here. Thank you.
Thank you very much, Francisco. I think it was very interesting talk, and despite we were a bit late, so I think that maybe we have time for a short question. There is, Tiziana, please.
Thank you very much. A very interesting talk, and it's new for me, so it's fascinating. I have one question regarding, at a certain point, you mentioned a cluster that you have performed. Mm-hmm. And could you please tell us what type of clustering did you use?
So thank you for a comment. So we use some T-SNAPE clustering aspects that basically try to cluster the behaviors based on their actions and regarding also the actions of the others. So depending on what happened before, what kind of reaction an individual has. So basically we clustered players using this type of arguments, and we tried several algorithms.
Did you also please check other clustering procedure?
Yes, we tried several procedures, and they all worked in very similar ways. Yeah.
And if Giulio allows me, just another question for curiosity. You were mentioning
Yes,
these rewards and punishments.
Yeah.
And my question is, do the institutions that you mentioned, including also educational institutions like schools, for example, because, you know, in different countries, high school, for example, they are implementing different types of rules for kids, like, you know, detention, and the rewards and so on. Are there any studies and do your institutions also referring to those?
That's a very interesting question. I don't know much about it, but I think it's very interesting to see, or also actually think about how to introduce some sort of education procedure in this context. I don't know how to answer, but I think it's a nice idea to follow for sure.
Thank you very much.
Thank you for your question.
So thank you, Francisco. I would have, a couple of questions myself, but we really need to move on because you know, time is running. And if someone has some other question, you can keep contact with Francisco, and I think he will be happy to answer. So let's
Thank you so much.
So thank you again, Francisco, and let's go to the second speaker, who is Konstantinos Ntinopoulos.
Good afternoon.
Yeah, please, the stage is yours.
All right. Good afternoon, ladies and gentlemen. My name is Ntinopoulos Konstantinos, and I would like to thank the organizing committee for giving us the opportunity to present our work. Our presentation is focused on financial bubbles, an area of interest since the birth of them, and we will focus on the Great Recession of 2008, when Alan Greenspan was called to answer for his choices regarding the monetary policies of the Fed and the crisis confrontation to the Congress in October 2008. Referring to his economic philosophy, he stated that he has found a flaw, and after some questions of his ideology was not right or it was not working, he stated, "That's precisely the reason I was shocked, because I'd been going for 40 years or so with considerable evidence that it was working exceptionally well." Identification, prediction, and acting against bubbles are the main research interests, but every bubble does not share the same characteristics with the rest. The only common characteristic they yield is the word reform that appears in aftermath market action. And why reform is always the needed action? Is that an evidence that bubbles or crises change the market structure? So, did Great Recession change the market structure, dynamics, and linkages? Furthermore, are there any variables or conditions that provide explanatory power in both pre- and post-crisis periods? These are some of the questions that we will try to answer. Our data concerns the United States and refers to two periods, 2000 to 2007 and 2009 to 2020. We intentionally left out the crisis period specified by Fed to be the period from January of 2008 to June of 2009. We follow this approach to compare periods of moderate stability, growth, and volatility. Moreover, we are aiming to extract results without the disturbances of the crisis effect. The variables chosen from the area of monetary policy, macroeconomics, financial markets, banking, consumption, and behavioral indicators such as excess reserves, multiplier, unemployment rate, exchange rate, long to short run spread, loans, and others in a total of 20 variables. We tried to choose variables from all the economic and market sections that were influenced by the crisis. Finally, Python programming language under the Jupyter Lab environment was used. The methodology initiates by calculating cross-correlation matrix and heat map presentation for both periods. Clustering based on the correlation values follows in order to reveal the linkage change. Moreover, in a try to shed light on crucial explanatory information, we imply principal component analysis in both periods to exercise vector autoregression analysis. Finally, impulse response analysis is revealing important findings concerning variables with explanatory power in both periods. We must state that in the heat map presentation output, with blue color is presented the negative cross correlation and with red the positive cross correlation. It is not in our purpose to provide for the presentation needs values interpretation, but we focus on color interpretation. Our intent is not examining the increase or decreasing of the correlation values, but the permutation from positive to negative cross correlation. In such a condition, we have an explanatory variable's structural reallocation, meaning that we are after total affecting change. Focusing, for example, on the variable circled, there are many such changes spotted. Variables proved to correlate in a totally different way before and after crisis. Crisis changed the way market links different sections, for example, oil prices and euro to dollar exchange rate, with most of our variables, or loans to major economic indicators. Continuing, we present variables clustering based on cross-correlation metrics for both periods. In the pre-crisis figure, upper in our presentation, we note that most of the underlying variables consist a large market cluster, as we circle. It seems that economy sections are very close and they move in harmony. In the post-crisis, the massive cluster shortens and market explanatory variables move to other clusters, as presented. The difference is that main economic indicators, such as oil prices and euro to dollar exchange rate, are clustered with behavioral indicators and crucial economic parameters, such as unemployment rate and long to short spread of Federal Treasury constant maturity. Probably, US market is more dependent on foreign markets in the post-crisis period. Finally, not only the size of the cluster changes, but also the structure of them, meaning that variables move from one to another cluster. Having already notable signs of structural changes between the two periods, our interest focuses on the explanation of the effect. To examine if there is any variable with sufficient explanatory power, we will imply impulse analysis. Prior to it, var analysis is needed, and to keep sufficient degrees of freedom, we sorted the number of variables by PCA. In the table presented, we provide all the needed information of the variables imposing PCA, the number of variables produced, and the explanatory power they yield. Moreover, we name the new variables produced by the PCA in order to make easier to follow on the forthcoming analysis. Generally, we could say that the results were sufficient and the method improved the analysis. Given that it is not possible to present the entire analysis results, we choose to present the analysis results of the excess reserves as major monetary policy instrument. In the graph, we present the way excess reserves changed during crisis. We must denote that the grey part of the graph is the crisis period as stated earlier in slide 3. We can clearly see the shift in the values before and after the 2008 crisis. The necessity of reserves led Fed to implement a strict monetary policy that led banking system to impose restrictions in lending money, decreasing the money multiplier and moreover the consumption. There are many articles about the significance of lending in growth and consumption. Moreover, there are more than few researchers stating that the ease pre-crisis monetary policy was crucial in inflating the bubble and the tight monetary policy afterwards re-establishing stability. But what are the reactions by implying a shock on excess reserves? In the graphs presented, we can see that a positive shock into banking excess reserves causes opposite reaction on the monetary index, which consists of the variables multiplier and Fed funds, and in the macro index, which consists by the variables long minus short spread of Federal Treasury constant maturity, real estate loans and unemployment rate. As stated earlier, given that banks decreased, the amount of loans multiplier decreased, and it is verified. In addition, a shock in excess reserves caused similar reaction on SP 500. we can say that although there are negative effects by implying strict monetary policy, markets, in our analysis SP500, need the presence of the government intervention. Investors need the Fed and generally the banking system's safety. We can say that excess reserves seems to be the parameter that shifts the saddle point of market equilibrium. It looks like the crucial variable that reallocates the market stability point in the multiple dimensional system. Further investigation of catastrophe theory as introduced by René Thom could be possible. But are there any other significant results on SP500 by the rest of the PCA variables? Considering the findings of cross-correlation matrices, where variables appear to face severe behavioral system changes, as well as the clustering output, where variables appeared to change clusters before and after crisis, we implied shock to the variables international, as named for the principal component analysis needs, after the variables of oil prices and euro to dollar exchange rate. We would like to remind that these two variables are the variables moved after crisis and they appear to be linked more with uncertainty and behavioral indicators. Therefore, implying a shock on the international index produces an opposite response on SP500 and similar response on uncertainty. Impulse response verifies the structural change presented in the cross-correlation matrix and in the clustering change of the variables. Closing, we can conclude that there is a structural change in the market after the Great Recession of 2008 crisis in the sense of explanatory variables effective weight and power. Our findings from cross-correlation change and clustering indicate our statement. As we already stated, we could probably think of it like René Thom described it in catastrophe theory. Probably there is no certain actions to be taken in the financial bubble generation period or even confrontation of it, but certainly we can spot important characteristics of the market system. There is evidence that Fed's choices affect the birth, inflation and explosion of the bubbles. From our analysis, SP500 is affected by the national market parameters like oil prices, exchange rate and uncertainty. Moreover, excess reserves are crucial in the operation of an economy as well as of financial markets, given that they present effects and reactions in the monetary level as well as in the investors' behavior and in the financial markets. Thank you for your attention.
Right. Thank you for the very interesting and clear presentation.
Thank you very much.
It was very smooth. Are there any questions from the audience? I think yeah, we have time for Tiziana.
Okay. Yes, thank you very much. And very interesting work. You were showing some plots with SP500 at a certain point with some curves. I didn't note if there were any error associated with your calculations and analysis. Did you compute any confidence interval, any error associated to your calculation?
Yes, we have made all the, first of all, we did the PCA analysis, then we ran a VAR analysis, and finally, the graphs you saw was from impulse analysis. During the VAR analysis, we did all the necessary tests, co-integration tests. We also did Granger causality tests in order the results to be sufficient. All the analyses presented are verified.
Thank you very much.
You're welcome.
Hi, I think I'm next. Should I start?
Well, I think we lost Giulio.
Oh, here it is.
Probably his connection. There has been a problem. Ah, Giulio,
Yeah,
okay.
Yeah, sorry, my connection went down. I don't know why. It was I'm widely connected, so it's, so have you done with your question, Tiziana? Yeah. Is there any other question from the audience? Okay, otherwise, sorry for the bit delay. I think we can move on to the next presentation.
Thank you very much.
Thank you, Konstantinos. And so now we have Neave. Yeah, hopefully I pronounced the name correctly.
Yes.
Great. So can you share your screen?
Yes, I'll have a go.
Perfect.
Yeah.
So the stage is yours.
Brilliant. Thank you so much. Okay, so this is joint work with Muhammed Yıldırm, who is an academic at Koç University in Turkey, and he was previously a colleague of mine at the Growth Lab at the Harvard Kennedy School, and Professor Ricardo Hausmann, who is a professor of policy and economic development at and the leader of the Growth Lab at the Harvard Kennedy School. So this is work that was predominantly done while Muhammed and I were fellows, postdoctoral fellows at the Growth Lab. And so I'm currently based at the Center for Advanced Spatial Analysis at University College London. Okay, so this work contributes to a large and burgeoning literature that suggests that the presence and diversity of capabilities embedded in the local workforce and in sort of the local economic structure constrains diversification and growth processes. So effectively, what you know how to do, the kind of inputs that you have available to you are the determining factors in deciding what you can do in the future, in the near future, and your growth prospects. And this might seem like a very obvious and intuitive idea, but actually it's something that has, only become embedded in models of economic development and growth within, say, the last 10 years or so. And so the key idea here that we need to keep in mind is that places tend to move into new activities. So they tend to expand their workforce. They tend to, move into sort of generate new types of firms in economic activities that are proximate to what they currently do. So for example, you can see in this little graphic, if you're currently producing yarn or wool, it's much more likely that you're going to diversify into the production of some kind of, potentially bags or clothing, rather than jumping all the way into, the production of chemicals, right? So your capability base, what you know how to do, the kind of inputs you have are suited to things that are proximate in terms of capabilities to what you already have. And so there have been a class of network models developed over the past couple of years that try to capture this idea that places diversify into new industries, new activities that are proximate to what they already do. One of the most well-known models is the product space. So the product space was developed by Cesar Hidalgo, Ricardo Hausmann, and co-authors. It's a very well-known model, and it's a network of products, and the products are connected. The edge weights correspond to some heuristic for capability overlap, right? So in this case, they use export data, and they effectively look at the pattern of co-exports. So if two products are effectively exported by the same set of countries, they sort of infer, in a sense, that these products require similar capabilities. So what we do in this paper here is we develop a mathematical model in order to estimate, in a sense, from a modeling perspective, a slightly more direct way of estimating capability overlap between products that's based on a modeling framework. And so what we end up with is a directed network that captures the sort of diversification paths of countries over time. And we are able to show that this network predicts better product appearances in export data compared to the product space. Okay, so I'm just going to give you a short overview of the model. So we can represent a country. So we can represent a country by a vector of capabilities. So imagine we had n capabilities. We don't know exactly what these are, and that's not important for this model. We just have n capabilities, and we can use a vector of ones and zeros to represent the capabilities that country n has. And similarly for product I, right? So product I is also represented by a vector of ones and zeros representing capabilities, and we can easily store, in a sense, or capture the capabilities required for product I. And so what we want to do is build a model that describes the probability that country N will jump into product I, will start producing product I. And so our model basically is a binomial model. And so we say that basically the probability that country N will start producing I is binomial with exponent, and the exponent is equal to the capability gap, right? It's equal to the number of capabilities required by product I minus the capabilities, the set of capabilities that country N already has, right? So in this case, there are 3 capabilities that product I requires that country N does not already have. Okay, so I'm not going to go into great detail into the model, but what we can do is we can decompose the probability, the capability vector of product I into, so if for example, country N already has a product J, okay, so we want to understand the probability of product I appearing conditional on the presence of product J. And so we can decompose the capabilities required by product I into those that overlap with J and those that don't. And we can express that probability of I appearing given that J is present in the second equation that you see there, right? So it's very similar to the past one, except we see that instead we're looking at these non-overlapping capabilities in the exponent. Okay, and so jumping forward slightly, we can express the capability overlap, which is what we're interested in. So the capability overlap between products I and J, which is the thing that we want to estimate, which is in a sense, the edge weight in our product network, the capability overlap between I and J, and we can express this in terms of these appearance, well, in terms of the log of the probability that J is present, given that I appeared, divided by the probability that J is present. So the next thing I'm going to do is give you a short example. So we can see here that we can easily compute this probability from data. So here we have a car, and the car appeared in 20 countries. And we can look at tires, and we can see, well, tires were very prevalent in the countries where cars appeared. So there's obviously a strong relationship between the presence of tires and the appearance of cars. So we can very simply plug in numbers related to the appearance and the presence of products into our equation in order to estimate the capability overlap between tires and cars and tires. Okay, so given that we can easily estimate this overlap from data, what we do is we apply this formula, and we apply it to international trade data, very similar to the product space, and we construct a matrix of capability overlaps between product pairs for the period 1984-2009. And this effectively is going to produce for us an alternative but directed product network. So we can look at the ecosystem of individual products, right? So if we think about, if we go back to the previous slide, we think about cars. Well, we can look at the overlap between cars and tires, cars and bicycles, cars and cattle. So we have a vector, in a sense, of relationship between cars and all other products. So we look at all of the non-zero entries in this vector, and that effectively is scenarios when there is an overprevalence, in the sense of the presence of, in this case, tires relative to what would be expected across all countries. And so the size, the ecosystem size, is the number of, in a sense, significant products in the ecosystem vector. And the ecosystem input of a product is the number of products that a particular product contributes to the ecosystem of, if that makes sense. So the size is how many products, you know, are typically present when product I appears, and the size relates to how many products is product J an input to. Okay, so we can see some examples here of large ecosystem size products. So these are very sophisticated products, typically have a lot of products are present in their ecosystems. And then input products are products that typically are present in the ecosystems of many other products. So they tend to be less complex things. Okay, so I'm not going to go into too much detail here, but suffice to say that, you know, we have ecosystems, we have particular products that have ecosystems that require many, many inputs. These are sorted vertically. So we have those across the top. And we see that products that require few inputs, so they have few products in their own ecosystem, these tend to be very common inputs. And this is just what this nestedness figure is telling you. It's telling you that basically when you have a product that has a small ecosystem requiring few products, those products in its ecosystem tend to be very common. They tend to be inputs to many, many different other products. And that's something that's kind of known as a phenomenon of nestedness in industrial ecosystems. There's a sort of adjunct literature on that. Okay, so what's very interesting is that products tend to either have a large size or a large input, but they tend not to be both, right? So they tend to either require a lot of inputs or be input to many things, but we don't see any points in the top right-hand corner, which is consistent in a sense with what we would expect. Okay, and similarly, as we would expect, we see that wealthy countries tend to have products with a large ecosystem size, so they tend to have complex products requiring many inputs, whereas poorer countries, which are shown in the yellow and orange dots, tend to have a much larger average ecosystem input, so that their products tend to have a much higher input value, meaning that those products are typically more found in the ecosystem of many other products. So this again is consistent with what we would expect. Okay, so as I mentioned, our matrix E that we've constructed gives rise to a directed matrix of products. And we can collapse this matrix using a community detection algorithm into subsections. So we can group various products together based on the connectivity structure of the network. And we just see that visualized in the inset. And so we can categorize, in a sense, these different communities. And we see the yellow one has many products that are high input products, right? So countries tend to start in this yellow cluster, and they tend to move in the network towards the left of the network, following the arrows. And this blue and green communities tend to be high ecosystem size products, right? So complex products. And so we can actually look at how countries change their basket of exported products over time, and they move from the yellow community towards the blue and green communities. So you see here, you see the share of products in each of these 5 communities changing over time. And you see that, wealthy countries tend to have a large and growing share in the blue, very complex community, whereas, poorer countries would have a much larger share in the yellow community, which is these high input products, which are much more like agriculture and sort of, basic sort of metals and things like that. And so we see that, obviously Singapore is very complex, whereas we see that, actually India has a decreasing but still a much larger share of exported products in the yellow community. Okay, so I've gone through this fairly fast, and this is the last slide, so we should be roughly on time. And so the main point here is that, one could say, well, this is very nice, interesting descriptive work, but why is it better in a sense than the product space? And so what we can show using a probit model, so here our observations are country product appearances, and we can show using a probit model that our network, in a sense, the structure of our network is better able to predict the appearance of products over time. And we have a statistically significant better prediction than a comparative metric based on the product space, which is widely used in a lot of literature. And so we would propose the facts that our network is based on a mathematical model for capability accumulation. It's a directed network which captures diversification paths, and it can outpredict the product space. Means that this is a viable improvement of the product space method, which is very widely used and embedded in policy making as well as academia. Okay, thank you.
Thank you very much for the very nice talk. So we have time for questions. You were very on time. So in the meanwhile that people think about their question, I have one. And that would be, do you, I mean, do you think you consider more or less, if I remember well, like 25 years of data, right? From 83 to, well, 2000 and something. Do you think you can, you know, try to detect if there are temporal changes of this product network? If you consider subsets, maybe you can go, you should consider more product. I don't know. I mean, maybe the data are not very, cannot do that, but I mean, can you comment on that?
Yeah, no, I mean, so this paper is currently in a late stage review, you could say. And we have got now, you know, actually a very, very extensive appendix where the data is cut in every possible dimension you could think of. So we certainly have split the data into many different time periods and looked at the kind of cross correlation in a sense between periods. And it moves for sure, right? Because the nature of production changes, but it's still reasonably stable. We don't see any big jumps, and you see as the more distant you get, the more dissimilar it is, but it's relatively stable, you could say.
I would say, yeah, at this level of aggregation, you have something like 700 products, right? Yeah. So I expect it would be stable. Maybe if you consider, I mean, more digits, or if you consider finer structure, maybe you can see some bigger movements. But I don't know. I mean, that's just my guess.
No, it's a good question, and something that we certainly have put some time and energy into doing that. Because we do, of course, aggregate. So the final prediction, it's like an out of sample approach. So we group all of the data up to 2009, and then we try to predict what happens after that. But we've also done a subdivision of all the grouping, and yeah, it's relatively stable.
Okay, thank you. We have another question from Tiziana.
Yes, my question, thank you very much. Really a very interesting talk. My question is linked with what also Giulio was mentioning towards the end about this digit. So you were showing your data, and if I recall properly, you were considering only 4 digits. And my question is if you also look at the different types of digits. A few years ago, I don't remember now, was 2018, I think, we published a paper in Entropy with it was a topical issue on economic complexity edited by Professor Pietro Nero, and one of my PhD students did this work on these products. And he was indeed looking at different data with different digits. And actually, you see some differences, especially when related to your plot about the nested. I cannot pronounce this word, nestedness. I cannot pronounce it. And we were finding differences in the plot that you saw. So I'm curious to know if you have done something similar as well. Thank you.
So we definitely did. We've definitely done some of the analysis at a higher level of aggregation, where we went to 2 digits. For some of the network, some of the actual network visualization, the visualization is actually at the 2 digit, but it's just aggregated for visualization purposes, as you know, the actual analysis is done at the 4 digit. So I think that the main issue there is really that, you know, generally these are very noisy processes, right? And so the more you subdivide, the noisier everything gets. And so if the R squared in the, you know, is sort of like 0.05, it's sort of typical, right? Actually, for these kind of predictions, you know, the more you subdivide everything, the less predictive power you have in all directions. And so, and I would say that the predictive power decreases relatively uniformly across products, but where you really see differences is if you subdivide the countries, right? So we know with the product space, if you have much better predictive power for poorer countries, because the product space says a lot more about constraints, if that makes sense. So whereas wealthier countries have a lot. I think the best way of expressing it is that wealthier countries have a lot more going on that you don't capture in these models, right? So the predictive power of these models starts to fall if you subdivide countries. I'm less familiar with subdividing products, but I think my expectation would be that if you go down in digits, you have a fairly uniform, just dramatic fall in predictive power. And I'm not sure if that varies across product category, if that makes sense.
Thank you very much. I will be happy to share our paper with you if you want.
Yeah.
You can see what we did. Thank you.
So thank you very much. again for the talk. It's time to move on. We are late, I would say. So next one is Jeremy Turiel.
Yeah.
Hello.
Hello. Just share my screen a second.
Yes.
Okay. Cool.
All right.
All right. Hopefully it loads up.
Perfect. Stage is yours.
We're all there. Okay, good. Yeah, thank you, everyone. So essentially, what we want to present today is a work looking at structure in financial markets and talking about filtering generative processes of the different time series in financial markets and how does this apply to portfolio risk. We also introduced several new concepts in how we study the change in structures in financial markets and new measures for portfolio constructions based upon that. Just wanted to point out this joint work with Paolo Barucca and Tomaso Aste from University College London. So just a general kind of outline idea. So temporal networks are generated in our case from exponential smooth and weighted correlations. We generate ensembles of null models with a different range of constraints that we'll talk about in order to compare the real data with the constraints. We filter correlation matrices with a TMFG as well as quantile thresholding, and we will discuss what that is. We then checked for what we call soft persistence of the motifs in time, so essentially higher order structures in these networks. We then analyzed the persistence of these time series null models and compare with the real data. We identify certain properties of these motifs in these particular persistent structures, and then we apply our findings to portfolio construction. So around motivation and objectives, essentially preferred diversification has been really a central theme since the 20th century in financial markets. So it's been very difficult to understand what sectors are and how do we diversify sectors. And then we identify these persistent motifs, which have essentially sectors with shared price drivers, so very peculiar sectors that we'll talk about. We also identify the idea that we should treat persistence and correlation very differently. A lot of people often get confused in finance around the idea of having correlation looking at persistence, and we talk about the idea behind filtering and why you should treat these measures differently. The nice thing is that this is an unsupervised technique with no tuning parameters. And then we verify the theoretical hypothesis around the evolution of market structures in time. So there have been a lot of claims around the fact that market structures change and they change slowly, but we haven't really seen in the literature much evidence of how they change and the fact that they do change slowly. And then we show the value of these higher order structures versus value-based filtering, so things that don't account for the whole network structure there. So talking about market systemic risk and sector risk, so not all sectors are the same and are persistently correlated. We see that strong correlations do not necessarily imply persistent correlations in time. So when you're trying to diversify risk, you essentially don't want to look at the stronger correlations only. You might want to look at structure as well. And then we see the motifs identify some more persistent correlation structures. We talk about market stability, and then we talk about diversifying these risks essentially based on the persistent motifs and persistent structures. And then we talk about the fact that motif chains, so a very large chain of higher order structures that are persistent, indicate the potential for systemic risk. Just a quick overview of the data. We essentially use data from 4 exchanges, which allow us to have an overview around liquidity and development of markets, and essentially generalizing our results to different scenarios and different systems. So the method, I'll just kind of gonna skip through very quickly. So it's a bit more technical, but just to have it on the slides. So we use those null models. We have 4 null models essentially. One is random return shuffling. Then we have a univariate Gaussian generator. So random return shuffling, we essentially generate the log returns and we just shuffle the time series. So it's an almost unconstrained, apart from the intrinsic volatility of the product, so the individual time series, it's almost unconstrained as a null model. Then we have a univariate Gaussian generator. So you essentially constrain the rolling mean and standard deviation of each univariate time series. And then there are the last 2 null models where you take into account the structure. So you either assume a stable multivariate structure, so you essentially fix the correlation matrix and generate from that, or you recalibrate rolling your correlation matrix essentially, so your covariance and your means, and you generate from that. So those are essentially 4 different assumptions around how markets evolve and how market structures are composed. So just skipping through those. Yeah, so the correlation matrix, we talked about having a rolling candle correlation matrix with exponential smoothing. The idea is that you have more stable estimations, but you also give more importance to the last data points. Talking about the filtering, so I just want to kind of settle on that. So we have the TMFG, which yields a planar graph, which tells essentially the plane with tetrahedral cliques with triangular faces. So essentially a tiling idea on a planar graph there. Obviously, you can go to higher genus, but that's obviously a different point there. But essentially, it's a topological constraint. So you're looking at the overall picture of your network as you form the network, whilst quantile thresholding is the opposite, is what we would call local. So although you have an idea of the distribution of values in your correlation matrix, you're essentially threshold on your value, which makes you very subject to not having an outlook around the network, so not creating, if you will, a homogeneous, well-behaved network. So just introducing the last theoretical point is simplicial persistence. So we've kind of discussed the idea that we look at persistence of motifs and we define this new measure, and just want to talk about what that is. We take edges versus motif persistences. Motif persistences are essentially higher order simplicial complexes. So there are things like triangles, tetrahedra, and etc. In these filtered networks. And then we analyze the decay form and the properties of those which are very persistent, so which are very present. Why do we talk this? Why would we talk essentially about soft persistence? Is the idea that normally people look at survival of motifs or edges in time. Whilst what we do here is we talk about soft persistence. So essentially, what if an edge or a motif exists at time t and at time t plus tau, we don't need it to exist all the way in between t and t plus tau, but it's enough that those two motifs essentially exist. The idea is that in very non-stationary and complex systems such as financial markets, you can't expect these structures to be as stable, and really you would lose a lot of the motifs with survival. So obviously then we look at motifs which are more persistent, so we eliminate the spurious part essentially, but it's important to not lose motifs just because you lose them at 1 of 2 time steps when you estimate your network. So this is just a bit more of that. So essentially, the last point I want to talk about is portfolio optimization. So we use a very, very simple measure. The idea is that a lot of people in finance look at 1 over vol. So they rebalance your portfolio essentially so they weigh the portfolios as 1 over the standard deviation. What we do here is kind of analogous, so trying to be very simple about it, but our measure is obviously not a local measure as volatility, but it's the persistence of the motif. So essentially, it's how much that node or that stock is central in a lot of persistent structures. So essentially, how systemic it is to an extent. And we want to reduce essentially the weight of very systemic stocks, which will cause very stable structures and hence volatility and risk in portfolios. Talking about results. So the first part that we want to point out is the power law decay. So we look at soft persistence of these complexes, and we look essentially at the memory of those systems. So we identify 2 regions. One is the decay region, as you can see here, and one is the plateau region. So as the decay region, you essentially have it finishing almost before the time of the estimation window for the correlation matrix. The idea is that you have a faster decay because there are a lot of spurious things which are going away. And then you have the plateau region, which is when you don't have any more overlapping data. And essentially you're really looking at the real structure, the real persistent structures. Obviously, this is way above any null model and shuffling. So it's highly significant from this point of view. So we do have existing structures. The interesting point is that we call this a plateau, but it's not really a plateau. You can see that from the fit as well. It's actually a decay. So market structures, once you've eliminated the spurious part, the real structure does evolve and evolves slowly. So here we're able to show initially already here, but we'll show it again, that those markets do evolve and they do evolve slowly and with a type of power law decay, which hence indicates long memory in those systems, which is a crucial statement from this point of view. So moving to the next slide. It just takes a second to load normally.
How big is this slide?
No, it's there.
Yeah,
Sorry.
this,
Yeah, I've no idea. I've tried to reduce the images in every possible way. It doesn't seem to work. So this slide is a bit of the problematic one, but it has very interesting results. So we kind of want to mention that. All right, so we talk about the null models essentially, and we talk about these null models of persistence. Now, what does it mean is that we have 2 or 3 clusters of these null models. We essentially have on the bottom part, if you look at edge or triangles, you still have on the bottom part the univariate null models, so null models that don't impose any structure when they reshuffle or when they generate. So essentially you see that to have persistence, you can't just have individual time series preserving their own characteristics, but you need to preserve characteristics of the structure, which is something that you would intuitively say, but it's kind of nice to have it shown. And then the nice thing is that you have in orange, you start having a thing that's generated from the rolling Gaussian. So you have a rolling estimation of your correlation matrix essentially, or your covariance, and then the means, and you generate from that. And on the top part, which is obviously stable once you've eliminated anything spurious, you have the fixed Gaussian. So essentially you generate time series from a fixed correlation matrix or fixed covariance matrix and means. The interesting point is that our real data, which is the brown line here, essentially sits in between the two. So essentially you are somewhat above what you would call just generating from a covariance matrix and means, which essentially would mean that if you just account for pairwise covariances or pairwise correlations, you cannot generate the same amount of market structure. So the market structure in real markets has to include higher order structures. And then what you also see is that it's below, though, the constant structure assumption, so that the structure does indeed change, does indeed decay, even after you've eliminated spurious stuff over here. One other interesting point that it shows is the value of topological filtering. Essentially, when you look at quantels, you have a very local estimation, and this works with edges. So essentially, when you talk about edges only, the things are as we expected. So the real one sits in between the stable and the null model, and that's fine. And that's the same for TMFG. But when you move to higher order structures, so simplicial complexes, which I've seen, and we will show again, that have a lot of value in portfolio construction and systemic risk, essentially quantels which don't account for the structure, they start struggling with that. So essentially you see almost no difference between the Gaussian, so imposing pairwise structures, and the real data. Because again, quantels are not able to capture that higher order structure. So it's not enough to look at local stuff. You need to start looking at higher order topological filtering, essentially where you account for the global structure before you filter. And then you see indeed in the TMFG here that the real data sits in between the rolling Gaussian essentially and the fixed market assumption. So so that's kind of just 2 takeaway points from this slide. So the idea that we do need topological filtering, we do need non-local filtering, and the idea that indeed markets do evolve. You can't just assume pairwise structures there. And yeah, so that's essentially that there. We just look at 2 last results there. So first, Markosification via decay exponent. So we look at more and less liquid markets and developed markets. The essential interesting point that we want to take away from there, just summarizing, is the idea that you have different markets, and actually you would expect normally that more liquid markets are more difficult to predict. What you actually find here is that more liquid markets are actually having a very stable structure, and the structure is actually simpler to predict. So if you will, this implies perhaps even more systemic risks. So the individual time series in liquid markets are very difficult to forecast, but the structures are way easier to forecast, and their structure is way stabler, which is a very interesting and perhaps counterintuitive statement there. And as a second point here, we show the value of triangular motifs. We essentially show that even when adjusting for the probability of the triangle existing as a function of the edges, these motifs are still persistent way beyond their individual components. So again, higher order structures are important. And here we just show how the temporal persistent motifs essentially in the New York Stock Exchange identify clear sectors in there, and in particular sectors with strong drivers such as pharmaceuticals and oil and gas. And as a last point, we just talk about portfolio volatility and systemic risk. So we just see that portfolios where you have the most persistent motifs versus portfolios of random stocks of the same size have way higher volatility out of sample. So essentially you have a method that's without any parameters, so any parameters you need to set, and it allows you to find highly systemic portfolios with strong predictive power, because again, we're talking about persistence in time. So the predictive power is intrinsic. And here you just see as the last thing, some results for our persistence weighting. So indeed, if you weight by persistence instead of by volatility, so you account for the global structure of the network, you are able to form portfolios with way lower volatility out of sample. So yeah, just conclusions are kind of around what we talked about. So we see long memory through the power law decays. We see that this persistence goes way beyond pairwise relations. We see the slow evolution of real market structures, the fact that they do evolve, but they evolve slowly, and the fact that this is highly relevant for portfolio volatility, and that weighting these portfolios by the inverse persistent actually helps outperforming standard methods in portfolios where you account only for local measures. So yeah, thank you.
Thank you very much, Jeremy. We have time for one short question, I guess. So let me see if there is some question from the audience. Otherwise, I have one. So it's very interesting what you show about the persistence. I mean, the power law shape and the Brando. So I was wondering. I mean, I guess you didn't have time to define what persistence is. Exactly, but so is that tau, I mean, a measure of days, first of all?
Yes, yeah. So I didn't have time to define and count the whole thing. That would be very long. So yes, about days. So we're talking about essentially 126 days. So you estimate your correlation matrix over 6 months with exponential weighting, and then you shift by 1 day each time. So essentially you expect in the first 100 days or so to have a strong overlap. So that's why I talked about the spurious part at the beginning.
Okay.
And then you start having, let's say, if you will, the non-overlapping part.
So I don't remember if you showed this, but maybe you have seen it in your research.
Mm-hmm.
Do simplicial complexes persist more than single links? I mean, just like a general question.
Yeah. So that was definitely on one of the points. So essentially, the idea is that if you assume that that edges are independent, and simplicial complexes, so triangles and tetrahedra, are so their persistence is just the result of the individual persistence of their edges, which is what we've shown. So essentially you say, it's like you say probability of A and B and C, probability of A times B times C, right? Something of the sort. So we tried that with pluses, so actually with generating even the networks based on individual persistences, etc. So it doesn't work. Essentially the persistence of the edges combined is way less than the persistence of the motifs. And right. If you look at identifying the most persistent edges, and then you form portfolios, or you rank them, or you generate the most persistent motifs from the edges, you don't get the same things. Which essentially tells you that, these perhaps are a bit more spurious. And then if you impose structure, which is what exists in financial markets, so you know that sectors are clusters or cliques or of higher order structures, then essentially you get more clean results, if you will. So yeah, so they're different things, and they're persistent beyond individual links, and that's kind of why the value is there.
All right, thank you very much, and thank you for the presentation. Very interesting. So we have to move to the last presentation, and first of all, apologize if you are so late, Ioannis, but those were very interesting. So the last presentation is from Ioannis Antoniades.
Correct. pronounced correctly.
Incredibly.
Okay, let me share my screen. Thank you very much. Oops. Okay, can everyone see my screen?
No. No.
Oh, sorry. So here I have shared. Share screen. Okay, again.
Now it seems to work. Yeah, now it's okay.
Okay.
Yes.
All right. Okay, thank you very much for being here. This is joint work done with Dr. Giuseppe Brandi and Professor Tiziana Di Matteo from King's College London, as well as Professor Magafas from the Complex Systems Laboratory of the International Hellenic University in Greece. I think at least two of them are here with us today. Towards a warning tool for financial events, like stock market events, you have to start talking from multi-scaling in financial time series. And the study of scaling in financial time system has been a field of investigation for many years now. Scaling in general can be characterized as, uniscaling, or when the topological structure of a time series is unifractal, or multiscaling when the time series is multifractal. Now, application of scaling studies in financial time series, especially from stock markets, they show that they definitely display multiscaling. And this is nowadays widely accepted as an empirical stylized fact of financial time series. One method to measure multiscaling in a time series in general is the method we call the generalized Hurst exponent method. Of course, there are other methods that have been largely applied in literature, like multifractal detrended fluctuation analysis, or wavelet transform modulus maximum, or the rescaled range analysis. In this study, we are going to use the generalized Hurst exponent, and I think it will be apparent why. Now, multiscaling in general can be attributed to either fat tails in price change distributions, or in general in changes in a time series, either linear autocorrelation of the absolute value of log returns, liquidity dynamics, or the nonlinear correlation between high and low returns generated by the different time horizon of traders. Basically, what this means is the multiscaling can have several sources, and depending on the time series, one or more of these factors become more important in determining the multiscaling. Especially in financial time series, it's not the linear autocorrelation that is important. Mostly the fat tails has been shown to be important in multiscaling, and the nonlinear correlation between high and low returns generated by the difference of strategies. Now, another very, very important thing, though, is that multiscaling is not static. It varies with time. That's because scaling is linked with changes in underlying market dynamics. So market is not stationary. It changes with time as the years go by. So it's expectable that multiscaling is also changing with time. So the question is whether the temporal evolution of measures of scaling, if they can be used as market indicators, issuing probably warning signal for future market events. as multiscaling depends on market dynamics, changes in market dynamics may be a signal for some future evolution. And of course, one such critical event could be a stock market bubble. Before I tell you what is the innovation in this study, I will go very briefly through the definition of what a general Hurst exponent is. Basically, what this formula is showing is if you have a time series X and you're taking the essentially the Q moment of the changes of the distribution, so you're taking the time average of the absolute change of the values over a time delay tau. Now this average over some over a length n of n points scales with tau as a power law, basically. And the exponent of this power law is the Hurst exponent. Now, if you're talking about the generalized Hurst exponent, this is just a function of a parameter q, which is essentially represents the moment of the price changes. Now, if q is equal to 1, this is actually the original Hurst exponent. And if q has other values, then we're talking about the generalized Hurst exponent. Now, about the physical interpretation of this very quickly, if h1, that is the h for q equals 1, is is greater than 0.5, it means you have persistent behavior in the series. That means that the dynamics move in a super diffusive way, so you're going faster away from an initial point. If h1 is smaller than 0.5, you have anti-persistent behavior or sub-diffusive behavior, meaning that you're going you're moving slower. And if you're approximate 0.5, then this is the diffusive behavior, the behavior of a purely random walk. In a sense, for any time series, and of course in financial time series, what this says that if h1 is greater than 0.5, you have a larger chance to have an increase of the value after an increase, whereas if h1 is smaller than 0.5, you mean it's more likely to have a decrease of the series after an increase. So you have or vice versa. And if it's 0.5, it's equally likely to go up or down after in the next day. Now, one quick note about what the parameter q is doing. The higher q is, the more the larger changes in the time series are weighed. So for a high q generalized Hurst exponents, they weigh the percentage change distribution tails more, whereas the low QGs weigh the percentage change distribution center. So if you want to see what the tails of the price changes are doing, high Q GAGs are important. Now, how do you measure multiscaling or uniscaling using GAGs? Well, there are several ways. Ones that have been used extensively in the literature is you're looking at the Q spectrum width, what we call the Q spectrum width. It's basically the difference between a Hurst exponent of a low Q value and the Hurst exponent of a usually high Q value. So if this width W goes to 0, then you have uniscaling behavior. This is because when you have a really random time series, then the Hurst exponent, the generalized Hurst exponent, does not depend on Q. It has the same value for all values of Q. Now, if you have multiscaling, the W is greater than 0. That's because usually the high Q Hurst exponents have a different value and usually lower than the low Q Hurst exponents. There's another way called the V proxy that has been used extensively in the literature. This is a different way to define multiscaling. Basically, since the function of age, since age as a function of Q is linear in all practical situations, it depends on Q like this, and B essentially represents the slope of this line. And if now B goes to 0, it means that HQ does not depend on Q. So you have uniscaling, and if B is less than 0, that's because the function QHQ in the exponent is concave. Then you have multiscaling. So how do you calculate generalized Hurst exponent time series? Well, what you do is you calculate for each value of Q over a sliding time window of some length, call it delta T, and you calculate the generalized Hurst exponent. And then you move to the next time window and you do the same. So what you're actually getting is a time series of GHEs from the original time series. Now, there's also a time weighing parameter theta that you can apply. I'm not going to stress this too much in this talk, meaning that you can weigh the recent past more than you're weighting the distant past when you're taking the time averages needed for the Q moments, so that you have the more recent past count more in the Hurst exponent. Then you actually must apply it a smoothing, and then you get a time series. And let me show you quickly what is a GHE time series that you get. This is the GHEs for Nikkei, actually. The time axis is for in trading days, and you see for various values of Q how they vary. Few things that you have to note, that you can notice here, is that when this pattern is very wide, you have multiscaling. When it's very narrow, you have uniscaling. So immediately you see that even multiscaling and uniscaling is interchanged in time. So there's a temporal evolution in scaling, a clear one. And also another thing to notice is that you have, in many periods, you have different behavior of the different Q Hurst exponents. So for instance, here you have a large drop in the large Q GHE, the Q equals 4, whereas the Q equals 0.1 or 0 or 1 GHE rises. So you have this sort of temporal patterns. So the coevolution of the different Q GHEs is not the same in all time periods, and this is an interesting fact. So what we did in the study is we actually calculated the time series of GHEs for various Qs for some major stock market indices, SP 500 and Nikkei, as well as some peripheral ones, the Athens stock market and Sensex, it's Bombay. And what we did is we actually developed a visual methodology, you may call it a tool, that algorithmically identifies particular temporal patterns in multi-Q GHE time series in a statistically significant manner. So we actually identify particular patterns in the temporal coevolution of the different Q GHEs, and see how, if these patterns tell us something about the underlying matter, underlying market. So the visual methodology involves three main things. First, you have to identify an optimum value for the time window delta T. The other, and we've developed a strategy for doing this. This is a big question, by the way. And also, in order to check for statistical significance of the identified patterns, we compare against a random surrogate series. So any differences that we see compared to the surrogate series are considered to be statistically significant. And this has to do a lot with the fact that you're using a finite time window to calculate your Hurst exponents. and that introduces some finite size effects. This is why you need to compare with a random surrogate in order to distinguish the statistical significant deviations from a random time series. And actually, also the visual methodology involves the relative time trends between extreme QGHCs, and you will see what this means in just a second. But before I show you that, a quick note about the choice of delta t. This is a big issue because if you make the length of the time window in order to calculate the GHG too small, you have very few data and you have a large inaccuracy, so a lot of finite size effects in the calculation. But if you make it again too large, then you're missing the dynamical evolution of the underlying market dynamics, which you actually want to capture in a short time scale. So it's actually a trade-off between how much of the variation of temporal dynamics you want to capture and the accuracy in calculating the Hurst exponents. And we developed a methodology to pick a sort of an optimum delta t that is not too large, not too small. I'm not going to go through the details, but here it shows that, again, by comparing with a random surrogate, we can find an optimum value. Here it's around 250 trading days. This is, again, some time series. These are raw time series for Q equals 0.1 and Q equals 4 coming from Standard & Poor's, just to show you the amount of error that there is in determining each individual time series. The plot above is the actual Standard & Poor's, and the plot below is the random surrogate generated from Standard & Poor's. And you can already see that the random surrogate, the different QGHCs are almost coincide, whereas already in Standard & Poor's you see differences, but these differences are not the same in every time period. So there are time periods where they are large and time periods where they're small. And let me just say a few things about the temporal patterns. So we actually identify various temporal patterns in how the extreme Q Hurst exponents evolve. And here you have basically three categories of scaling, as we have named them. You have symmetric multiscaling when the extreme QGHCs evolve together parallel to each other, as you can see, for example, here and here. And you also have this sort of asymmetric multiscaling patterns we call A0, A plus, and A minus, where the different Q Hurst exponents show different trends. So they either, so an A minus, for example, is here when the high Q Hurst exponent drops faster than the low Q Hurst exponent, and that's an A minus, or the opposite is an A plus, as you see here. And you have also the sort of symmetric A0 when the low Q Hurst exponent rises and the high Q Hurst exponent drops at about the same rate. So we think that all these patterns actually mean something in terms of scaling. So we developed this sort of rigorous methodology that checks these changes in trends, compares them against what is expected for the random surrogate, and when it finds some statistical significant deviation, then it registers a particular temporal pattern. And here,
sorry, Ioannis, you should go to the
I should go
cannot
very
make your gestures, but yeah.
Yep, sure. So just to quickly show you some results, here you have the application in Standard & Poor's, and its color here represents a particular pattern of the ones that I was telling you about. But the interesting thing here is to see what happens in periods before, in critical market periods, like, for example, the development of a stock market bubble, like the 2000.com bubble that you can see here in Standard & Poor's. And there we actually see a transition from uniscaling to multiscaling that is happening usually through an asymmetric temporal pattern. You see the same thing before the Black Monday event. And let me show you a zoom of this behavior. So for instance, here is the dot-com bubble, and you see that before, while the bubble is in development, you have a transition from uniscaling to this sort of asymmetric multiscaling. This is the red line here, and a large multiscaling value. And then you may go back to uniscaling, but right before the bubble breaks, you go again always to multiscaling, as you can see here, and it's also asymmetric multiscaling. You can see the same thing in other periods in Standard & Poor's. This is 1936, this bubble, again, asymmetric multiscaling before that. And you can also see in other periods, like in before 1962, Standard & Poor's, Nikkei also. This is the 1990 known Japanese stock market bubble. And again, you see this pattern here going through asymmetric multiscaling. It's also very interesting to notice for the Nikkei and also Standard & Poor's, before Black Monday, you had a very strong uniscaling behavior. And right 1 year before Black Monday event, you had this sort of tumultuous multiscaling behavior. This is also true in Standard & Poor's. This is Athens again. This is the Athens bubble, and you can see the transition from uniscaling here to multiscaling. Another bubble that was in Athens in 1990. Again, you see this sort of multiscaling behavior. Notice also that before the 2008 bubble, we have a sort of a different behavior. This is an exogenous bubble. It's not purely stock market caused by the US real estate crisis. Here you have uniscaling behavior before, and just before the bubble breakdown, you're switching again to multiscaling. That's actually about 6 months before the collapse. So very quickly, the main results of the application of this GHE visual TP identification methodology. So in a critical market period, in the rising period, we have a transition from uniscaling to multiscaling via usually an asymmetric temporal pattern of minus type. Before a bubble breakdown, there's always multiscaling, and there's sometimes a transition from uniscaling to asymmetric multiscaling. There are some difference between a pure stock market bubble and an exogenous bubble, asymmetric multiscaling of minus type is related to anti-persistent behavior, preferentially for large price changes during a persistent market. A fact that we connected to a nervous market behavior during a rising period of a bubble. Basically, what this says is that when you have a stock market bubble under development, market players are usually nervous. So if there is a large drop, it's usually followed by a large rise, probably the very next day, and that actually causes the large Q Hurst exponent to drop, whereas the low Q Hurst exponent is not affected. That's why you see these asymmetric patterns, we think, before bubble formation. So I think I've exceeded my time a lot. I will have to say thank you here, and I will welcome questions.
Yeah, thank you. Thank you, Ioannis. Is there any question from the audience? Yeah, so I actually had one question, but you basically answered me with this, last comment of yours. So what is why this, multi-scaling behavior should arise? But you answered that, it's just related to this, nervous behavior of, let's say, large changes, which are correlated. Do you think that you have, I mean, is there any way to verify this hypothesis?
Well, actually, I didn't have much time to show you, but the asymmetric patterns before the bubble are attributed to two things. Either you have some really extreme tail events, like for instance, before the 2000 dot-com bubble, you had the so-called Russian crisis, and you had the Asian crisis that occurred in 97 and 98. These gave rise to very large drops in the market within one day, followed with of course, with a big rise in the next day. So this will create this, even, you know, these 2 or 3 single events will create a large bias in the high QG Hurst exponent, and it will show in the pattern. Now, actually, what we did was we took these events away. So we subtracted from the time series just a few days to see what will happen. And indeed, these patterns went away, but still you had some resilient multi-scaling. So before a bubble break, so you're expected to have either very large tail events, which you may attribute also to the fact that you have a market that is saturating, but also you have smaller events, let's say changes in the area of 2 or 3%, followed by large drops of 2 or 3% that take longer. There are more events and they take longer to occur. This is really the market nervousness. So both of these exist before bubbles to a lesser extent. For instance, for Athens, the Athens stock bubble in 2000 was very much, let's say, robust when you subtracted the Russian crisis and the Asian crisis. So even after subtracting these tail events, it still preserved the big asymmetric patterns, showing that Athens was a really, really, really big bubble. This is not so true with Nikkei or Standard & Poor's, for instance. It's true to a lesser extent.
All right, thank you. I don't see any other question. I think that
just if I can, I want to mention that the paper has been published in Physica A for people that might be interested. They find the full paper there.
Yes, I would like to say, sorry, Chair. My name is Magafas, Lykourgos. I'm co-author of this work with others, with Tiziana. The main concept of this type of works is based on the fact that the global capitalizations of stock markets, and when I say stock markets, I mean derivatives, mutual funds, shares, mainly derivatives. It's about total capitalization about 15 times greater than the total global GDP. That means an extreme event in stock markets affect the life on the earth, everybody. Our work is to find tools to detect extreme events in stock markets. This is the main concept of econophysics of this type of works, okay?
Yeah, sure. I mean, you're right. Okay, so if there are no other questions, I think that we are just a few minutes late, like half an hour, but you know, the session was really intense. We went from game theory to through economics, economic complexity, then time series analysis with simplicial complexes and the Hurst exponents. So really, I mean, big session. So thanks to all the speakers and to all the participants for being here virtually. And so let me just say, enjoy the rest of your day. If it's time for dinner, enjoy your dinner. If it's another time. Enjoy the rest of your day. And yeah, see you tomorrow.
Thank you very much.
Goodbye.
Bye-bye. Bye, Tiziana.
Thank you.
Bye. Thank you.
Bye-bye. Thank you.